Good morning, everyone. My name is Ya, and it's my great pleasure to present. Thank you. And it's my great pleasure to present our work on finding unguarded gates to bypass CFG with big data. So even though I am the only one presenting today, this one is really a teamwork with my colleagues, Kasang, Yanhui Zhao, Xiaoming Song, and Xiaoning Li. We would like to share our learnings with you guys and also at the same time to collect feedbacks from the security community. We are based in United States, but originally we all come from China. This is the agenda of my talk today. So firstly, I would like to quickly go over CFG and its implementation. And after that, I will quickly go over some previous CFG bypass research work. After that, I will talk about our research focus, our analysis approaches, and some results that we obtained using our method. After that, I will quickly talk about the fix for the issue from Microsoft and some future work that will be carried out. Okay, so first, CFG implementation overview. So as you may know that CFG is a mitigation technique that is used to prevent control flow being redirected to unintended locations by validating the target address of any indirect branch before it takes place. So the implementation of CFG would require the support from both the compiler and the operating system. For example, the compiler will need to insert a safe check function call before each indirect call and before each indirect jump. The compiler will also need to generate safe function table to list all legal entry addresses. And in addition to those two, the compiler needs to add CFG-related entries in load configuration table. Those include God safe check function pointer, God safe check function table, God safe function count, and the God flags. So meanwhile, the operating system supports CFG by point the safe check function pointer to this function in NTDLL library. It also generates CFG bitmap when the process is being created, and the bitmap is basically based on the safe function table from the compiler. So in addition to that, the operating system will also need to handle violations when a CFG check fails. So this picture more or less reiterate what I just said with a little bit more detail. So for example, the compiler inserts God check ICALL function pointer before each indirect call or each or indirect jump. The compiler need also generate safe function table to list all the valid entry addresses. Meanwhile, the operating system does the bottom half of this picture. The operating system points the safe check function pointer to this function LDRP validate user call target, this function in NTDLL library, and the operating system generates the CFG bitmap based on the safe function table from the compiler. And if the target address of the indirect call is valid in the CFG bitmap, it will continue this indirect call. So a CFG basically plays a role of officer, the road officer who checks Mr. Indirect Call's target address from its database. Basically, it's the CFG bitmap. If the target address is valid, the road officer would raise the barricade to let Mr. Indirect Call keep on going. So that's a quick review of CFG implementation. Now I would like to talk about some previous work on CFG bypass. So this one is a incomplete, we believe it's an incomplete list of some of the previous research work on CFG bypass studies. So for example, Yunhai Zhang presented his work on bypass CFG comprehensively in 2015 Black Hat USA. And while all these files are related to JIT compilers, and we also listed a incomplete list of attack surfaces, and most of these attack surfaces have already been mitigated. For example, non-CFG module. If a non-CFG module is loaded into the system, this module would become a weak spot that can eventually lead to CFG bypass. But we think this attack surface will eventually sunset with wide implementation of CFG. Indirect jump, this attack surface has already been mitigated by CFG the same way as indirect calls. Return address on stack, this attack surface has already been mitigated by newly introduced RFG, return flow guard. One more attack surface, the guard check echo function pointer inserted by the compiler before each indirect call or indirect jump. So this function pointer is supposed to be read-only, but under certain cases, it can be made writable. This basically is Yunhai Zhang's work, and this issue has been reported fixed by adding a wrapper to virtual protect. So 3 more attack surfaces are listed here. Set jump, long jump, because the jump buffer can be modified to bypass CFG, and this attack surface has been mitigated by long jump hardening in Windows 10 CFG improvement. GTD code, I'm going to talk about this one a little bit more in details, because most of the research work, previous research work are in this area. And finally, valid gadget. Okay, so 3 JIT compilers have been reported to have some issues that can lead to CFG bypass, and all of them have already been fixed. The CFG bypass method include using unprotected indirect call or indirect jump from the JIT code, using JIT spray because there's no target address check for indirect call or jump into the JIT code area, and lastly, by overwriting the temporary JIT native code buffer. I'll give you an example on each method listed here. So the first attack surface, using unprotected indirect call or jump from the JIT code, I listed 3 research studies on this method. Please note that all these 3 are related to register-based indirect calls or indirect jumps. So we have a call EAX here. We have a jump EAX here without CFG protection. The second one, using JIT spray, because there's no target address check for indirect call or indirect jump into the JIT code. It's all listed, like the address is all listed valid in the CFG bitmap. And lastly, CFG can also be bypassed by manipulating the JIT code in the temporary code buffer, which is writable, before it gets copied to the executable memory. I list the 1 research work on this attack surface. So lastly, valid gadgets, because CFG only prevents the control flow being hijacked to unexpected locations. It does not stop the unintended use of valid gadgets at legal entry addresses. However, with CFG, the availability of those gadgets has been largely reduced, making it very much more difficult to exploit. So those are the previous research work on CFG bypass. Now I'd like to jump into our research focus. So being different from all the previous research that has been done on CFG bypass, we are trying to probe this topic from a totally different angle. So instead of trying to break the CFG check logic itself or exploit the implementation issues of CFG in JIT compilers, we focused on another aspect that has not been widely, extensively studied before. So we focused on memory-based indirect calls. We actually reported our findings to MSRC, and we really appreciate the recognition from the bug bounty program as listed here. So this table is not updated yet because we reported 2 different issues to MSRC, and both were recognized. However, only the first one is listed on the website. Okay, so our research focus. So we basically treat memory-based indirect calls into 2 different groups. The first one is that the function pointer of the memory-based indirect call, the function pointer is located at a vulnerable memory location. So here, vulnerable means writable. So I'll give you an example. By calling a function pointer which is located in the data segment, so which is writable at runtime. So in this case, the compiler, when CFG is turned on, the compiler will insert CFG check for the target address before taking this memory-based indirect call. So alternatively, the other one that the other kind of indirect call, memory-based indirect call, is that the function pointer is located at a safe memory location. Here, safe means not writable. So for example, by calling a function pointer from import address table, which is located in the iData segment, which is read-only after being initialized at runtime. Because the function pointer is read-only, even though the CFG is turned on, the compiler would not insert a safe check function before this memory-based indirect call takes place. I'll give you an example on each case here. On the first one, the function pointer is located at a vulnerable memory location. So as you can see here, we have a memory-based indirect call my function pointer, and the function pointer is located in the data segment, which is writable from IDA static analysis. So when CFG is turned on, so basically it firstly move the target address to EAX and then move EAX to the stack, and then insert guard check ICALL function pointer before calling this one from the stack. So it changes, the format has changed from a memory-based indirect call to calling from the stack. So alternatively, on the second one, the function pointer which is located at a safe memory location. For example, we have a here we have a memory-based indirect call while the function pointer is located at the iData segment, and the iData segment is read-only from IDA, and which is confirmed from runtime analysis. Here, the function pointer is read-only. So in this case, even though CFG is turned on, the compiler doesn't insert safe check function before this memory-based indirect call. So basically, CFG, like a guard, protect each indirect call or jump. As previous research has shown that the register-based unprotected indirect call or indirect jumps are able to bypass, those are in JIT code, most of them are in JIT code, are able to bypass CFG because there is a gate here. However, for those memory-based unprotected indirect call or jump, cannot bypass CFG because there's no gate here, because the function pointer is not writable. So we started to think, is this really the case under doing runtime? So that basically is our research focus, trying to find a hidden gate. Basically, our research focus is to find the hidden gate, which means we're trying to find a memory-based indirect calls with writable function pointer at runtime. So that function pointer is not protected by CFG. So that is our research focus. Now let's talk about our research approach. So in order to find those memory-based indirect calls with writable function pointer, we utilized a PMU feature, PMU-based instrumentation tool to collect the runtime context information that we are interested in that can help us identify those memory-based indirect calls with writable function pointer. We also used a Spark-based big data analysis system to screen, to analyze large volume of data. So this PMU feature was firstly introduced in the Pentium processor with a set of model-specific performance monitoring counter registers. So it allows the selection of processor performance parameters to be monitored and measured. This is an example of IA32 performance event select register. This is the layout. The event number and the UMask value defines which processor performance parameter is to be monitored and measured. So, and we developed this framework to try to collect useful information that can help us look for those memory-based indirect calls with writable function pointer. So by programming a set of model-specific registers, each indirect call in the target code would trigger a PMI, performance monitoring interrupt. So each indirect call triggers an interrupt. And then we registered our interrupt handler basically through two different ways to collect context data, context information that we are interested in. Because the handler print out the binary code that we are interested in kernel mode directly, we had to be very careful to deal with page fault problem to avoid any page fault problem. So the handler is registered by two different ways. The first one is to hook the feth item in IDT table directly, while the other one is to use a Windows API, which was mentioned in more details by CPS in last year's Black Hat USA. I'll give you an example. We on our study was based on a Sandy Bridge type CPU. So in our study, we had to program the UMask value and the event number to be A0 and 88 respectively, so that, as you can see from here, each taken speculative and retired indirect near call would trigger an interrupt. And then the code stream that we are interested in at each legal entry of indirect call is collected by the event handler for analysis. So what kind of data we collected for on our study? So there are three addresses are involved on each memory-based indirect call. So we have a from address where this memory-based indirect call takes place. We have a function pointer, and then we have a target address where this function pointer points to. So, so each address has its own PTE page table entry. So basically these 8 pieces of information are collected upon each memory-based indirect call. So again, we collect from address, so from where this memory-based indirect call takes place. We then collect from code block, so we collect 8 bytes of information from the from address. And then we collect the PTE of the from address. After that, we collect the function pointer itself and the page table entry information of the target function pointer. And lastly, we collect the target address where the to address, basically the target address. We collect the 8 bytes of information on the target address, and lastly, we collect the page table entry of the target address. So 8 pieces of information are collected on each memory-based indirect call. So give you a real example of what we collected. So again, this is the data format we collected. So 8 pieces of information from address, from code block 8 bytes, from address PTE, function pointers address, function pointers PTE, to address, basically the target address, to address code block 8 bytes of information, and to address PTE. So this is the real data we collected. So for example, the first one from address 72A6 BD4B. At this address, we have a memory-based indirect call called UART pointer here, and then we collect 8 bytes of information from the from address. So as you can see, FF15. So this then followed by a address. So we collect this information, as you can see, FF15, E401, 01 AB72. After that, we collect the PTE from the from address. Okay, so and after that, we collect the target pointer's address, which is basically this address. It's address followed by FF15, 72AB01E4, which is listed here, and then we collect the PTE of this address. And finally, we'll collect the target address. So if you DD this function pointer, you get the real target address 75043CD0 as listed here, and the 8 bytes of information from the target address. So as you can see, 8BFF55 and 8BEC. So the target address, a code block, almost always starts with 8BFF55. So move EDI, push EBP, then move EBP, ESP. And finally, we collect the PTE of the to address, the PTE of this address. So as you can see that when we collect data on this much of data on each indirect calls, and there are millions of indirect calls, the data file size goes up very fast. And that's why we need a big data system to help analyze the data. This is the processing pipeline, data pipeline in Spark. So once we have that big chunk of data, we load it into this system and pre-process it to remove all the duplicates, because there are so many duplicates, memory-based indirect calls. After that, the code blocks we collected from the from address and from the to address are disassembled by Capstone. The purpose of this is to filter out all the register-based indirect calls, because we are only interested in memory-based indirect calls. After that, we check if the memory is writable through its PTE. So this is the very key point, the most important part of our study. Is to check if a memory is writable through its PTE. And once we got that, we had to go back to the program to identify to pinpoint which memory-based function in which library has a writable function pointer on a memory-based indirect call. Yeah, because that's our research focus. Basically, it's to try to find any memory-based indirect call that has a writable function pointer. No, because those register-based indirect calls we don't want to look at. Yeah, so we only look at memory-based indirect calls. That's why we just filled it out. Yeah, that's why we need to collect the code block from the from address, right? Yeah. Okay, so so let's talk about some results we obtained using this method. Okay, so we using the analysis method we just mentioned, we collected on Edge and IE. We collected about 70 million of indirect calls, and the data file size is about 4.4 gigabytes. After filtering out all those register-based indirect calls, we ended up, and all the duplicates, filter out all the duplicates, we ended up with a unique combination of from and to address about 20K. Also on Flash, we collected about 9 million indirect calls, and the data file size is about 600 megabytes. So after big data processing, we ended up with about 700 700 calls. So we found three cases. Okay, three cases out of, if you add them up out of 100 million indirect calls. So 3 out of 100 million calls that those three cases of memory-based indirect calls had writable function pointer, so they were not protected by CFG as per policy. So 2 cases had the function pointer which are located within the data segment, and those are in Windows.storage and IEAP FLTR library, respectively. Alternatively, the last case is very interesting because this one had a writable target function pointer which is located in the iData segment instead of in the data segment. This one is very interesting. As I'm going to explain each case one by one, 3 cases in total. So the first case, in Windows.storage library, at here we are able to find a memory-based indirect call called dword pointer, where the function pointer is located in the data segment, and this function pointer, if you check the address attribute, is writable, and the CFG check was not in place. So this is our first finding. The second one, very similarly, in IEAP FLTR library, at this address, there exists a memory-based indirect call calling the function pointer, and this function pointer, which is also located in the data segment, and if you check the address attribute, this one is also writable. So 2 cases, both had writable function pointer in the function pointers are located in the data segment. The last one is very interesting. Instead of having a function pointer located in the data segment, it's located in the iData segment. And if you read this name of the DLL, you can read out it's like Microsoft catch the flag. So we did catch this flag. Interestingly, if you look at this address, we are able to find a memory-based indirect call that had a function pointer writable, as you can see from here. So I said this case is of more interest because the whole IData segment, in this library was writable, as you can see from either static analysis. So this is very interesting because remember the guard check ICO function pointer inserted by the compiler before each indirect branch takes place. This function pointer actually itself is located in the IData segment. So which means that this function pointer itself can be modified because as you can see from here, we have a CFG check function pointer before this indirect call, and the function pointer of itself is writable in this DLL. So actually, the previous work showed that people had to really spend the time and make an effort in order to make this function pointer writable. But in this DLL, every single CFG check function pointer was writable. So we don't have to do anything, it's already writable. So we reported this finding to Microsoft, and after that we started to think this might not be the only library that had a writable IData segment. We then carried out a more thorough screening using a static PE analysis using Python script to screen for any writable IData segment in all Windows DLLs. So this is just a snapshot of what the Python script prints out. Interestingly, we scanned 4,093 Windows DLL files under Windows 10 32-bit system, and we were able to find four more DLLs that all had the IData segment writable. So using DDRAW DLL as example, as you can see from here, from IDA, the whole IData segment was writable. So that means all the CFG check function pointer can be modified on these four libraries. So we then scanned Windows 10 64-bit system and we found the same result. So basically we reported all these findings to Microsoft, and those issues have been fixed. So now let's talk about the fix for these issues. So actually Microsoft fixed these issues early this month. So I'll give you an example using MSCTF library as an example before the fix. As you can see that the IData segment was writable, and after fix, they are writable no more. They are no longer writable. This is also confirmed doing runtime analysis. The function pointer is now read-only. So basically, those are our research work on this topic. So I would like to talk about some future work that will be carried out soon. We believe that the PMU instrumentation data collection plus big data analysis is a very powerful framework and can be used for different bypass studies by selecting different policies with the same data set we have collected. So remember, we collected these 8 pieces of information upon each indirect call. So on our current work, we used data number 2 from code block and data number 4, the target function pointer, And data number 5, the PTE of the target function pointer to look for unprotected memory-based indirect call, which had writable function pointer. So alternatively, we can use data number 7 to code block to look for valid gadgets under CFG. And in addition to that, we can use data item number 7 to code block to look for unguarded indirect jump in the to code block. And lastly, we can apply data number 3 and data number 8, the PTE of the from address and PTE of the to address to look for cases with both writable and executable memory address, which could be also considered as a CFG bypass. Okay, so in summary, CFG is a powerful mitigation technique that effectively increases the difficulty and cost for memory corruption exploitation. Being different from multiple previous studies reporting CFG bypass approaches, our work focused on finding memory-based indirect calls with writable target address pointers, which can be exploited for CFG bypass. PMU, performance monitoring unit-based instrumentation and big data analysis are used for data collection and analysis, as well as static PE screening. We found multiple results and we reported to MSRC. And lastly, PMU instrumented data collection plus big data is a very powerful framework and can be used for different bypass studies by selecting different policies with the same data set we have collected. So with that, I would like to thank you all for coming here. And especially, we would like to express our acknowledgement to Haifei Li and Rodrigo Branco from Intel for their review of our work. And so this is the reference list in our presentation. And thank you.